Hello, everyone. Welcome to the fifth and final installment of CUAHSI's 2018 Fall Seminar Series. Thank you so much for continuing to tune in. I'm really excited about our talk today. Some housekeeping items before we begin. I'm Catherine Schleff. I'm a postdoctoral researcher with CUAHSI and the one who organized this series. The talk will be around 45 minutes and there'll be time for questions at the end. So definitely be thinking about those and then I'll moderate them. So if you have any issues during the talk and, technical issues, please feel free to chat or put your hand up, either me or the CUAHSI organizer, and we can try to help you resolve those. Now, that aside, it's my honor to introduce our speaker today, Dr. Patrick Ray. He's an assistant professor in the Department of Chemical and Environmental Engineering at the University of Cincinnati. And he earned his bachelor's degree at the University of Massachusetts Amherst and his master's and PhDs at Tufts University in Water Resources Engineering. He has spent significant time doing research in Jordan and Yemen and was a professor for some time at George Fox University in Oregon. And then as a postdoc and research assistant professor at UMass Amherst is when I got to meet him. In addition to working on really interesting projects that have wide-ranging scope and cover the US to Nepal, Patrick has a strong gift of hospitality. He's full of energy, which I'm sure we'll see in this presentation, and has a knack of saying something funny to lighten situations. So I've been very grateful for the mentorship that Patrick has provided me over the years that I've known him, and I'm excited to see the direction of his research now. So Patrick, thank you for agreeing to give this talk, and please take it away.
Great. Am I on? Everybody can hear me okay?
Yes, I can hear you.
Wonderful. Okay, so to orient everybody to this talk, Catherine did a wonderful job introducing it. Thanks, Catherine, for that. I've got something like 36 slides, and I will do my best to present them in under 45 minutes because I think it really would be fun to discuss this stuff with you. I am the fifth, I guess, and final, installment of these talks. It's very likely to be the worst of the five. So my apologies to all who have heard the other five, because I know the other four, because I know the other speakers, and they're outstanding. I will do my best to rise to their standard. What I'm going to talk about today, I've tried hard not to be too redundant with other things that you've heard in this seminar series. So I'll concentrate on hydropower because I'm fascinated by it and I've been learning a lot about it in the last few years and I'm getting more involved. And shout out to Ethan Yang, who gave a talk on this series recently, a couple of talks ago. And he really did a lot to introduce me to hydropower and how to analyze it in the first place. So some of this some of it is work that I did together with Ethan a few years ago on the Upper Arun project in Nepal. And a lot of it takes off from things that he introduced me to. So I will jump right in here to this. This is wanting to ground the sort of problem that we're dealing with in the whole world of problems that one could deal with. I like dealing with water systems planning problems under uncertainty, and we're going to talk specifically about hydropower because these are some of the very biggest problems in the world. Maybe you've seen this sort of slide before, but the World Economic Forum puts out global risks landscapes every year. This is the most recent one, 2018. And what it shows in the upper right quadrant of this slide on the left, can you see my cursor, by the way, if I move this around?
Yes, we can see your cursor.
Awesome. Okay, so here is, let's look at this box on the left, the global risk landscape. This is the likelihood on the x-axis and the impact on the y-axis. So this quadrant here is both high impact and high likelihood. So this is the ranking put out by business people in the world, Davos kind of people, right? Who think about, they think about what are the problems of greatest concern to their businesses, to their ability to manufacture well and export and all those kinds of things that they do. And what they've identified is a lot of green stuff here in the upper right quadrant. Isn't it interesting that most of these diamonds are green? When we look at our little legend of colors here, green is environmental. So of all the risks that that big time business people are most concerned about, the green ones, the environmental risks are most prominent. And of those, these sort of top three in the upper right quadrant, extreme weather events, natural disasters, and failure of climate change mitigation and adaptation are the particular emphasis of my work and others who have worked along my side over the last number of years, including many who have given talks in this series. So we are dealing with these really huge problems, and we deal with them with something called systems analysis. We make computer simulation models, and we run those simulation models many times to trace out the problematic conditions for the infrastructure or the policies that we are implementing on the ground. And I'm going to go ahead and call them water infrastructure, because that's the focus of the work that I do, is water infrastructure and water policies. But these don't have to be water infrastructure and water policies. They could be transportation. You build roads, those roads are subject to flooding and subject to overheating. Could be telecommunications infrastructure, could be anything, but certainly systems analysis is not limited to water, but that's how we apply it here. And systems analysis allows us to do this thing, this trade-off analysis. And trade-off analysis is the heart of what we're aiming for. We understand that we're talking about benefits and we're talking about costs. We're talking about building things on the earth that we need because they give us benefits, and likely everything that we build on the earth is going to have some sort of downside. If you build a dam, obvious downsides. If you build a road through a nice pristine forest, downside. But we want to understand how to weigh benefits versus costs so that we can make really good decisions, and that's what systems analysis does. Finally, of course, we can do risk management with systems analysis by running all of these scenarios and seeing which combinations of conditions give us the biggest problems, and then managing those things by trying systematic adaptation strategies. The takeaways from this talk are going to be that hydropower has obvious negative attributes that we all know. When you build a dam, everybody knows that that's a big problem. And the World Commission on Dams in the year 2000 made really painful statements about the uselessness of many of the dams in the world. So we're all well attuned, I think, in the last 20 years to thinking about the negative attributes of dams and hydropower projects. But I want to offer that hydropower has maybe underappreciated qualities of essential importance to our climate change problem. And I'll get into that in greater depth in a moment. The International Hydropower Association, headquartered in London, is teaming with the World Bank and the European Bank for Reconstruction and Development to try to develop guidelines for resilience, especially to climate change, but to other things as well. Vulnerability to climate change is not necessarily the vulnerability we need to care most about. It could be that the vulnerability is more to political problems or earthquakes. Earthquakes, of course, are a huge problem when you're building dams and mountains. You can't spend too much time understanding place and context. We really want to be bottom up in the way we approach these problems, and we want to represent stakeholder needs as well as we can. And it usually all rides on our ability to cooperate. Another shout out to Ethan Yang. He's an agent-based modeler and knows about cooperation in these models. We often find that that the goodness of our water infrastructure has everything to do with how well we can share the benefits and distribute the costs. But before we get too into worrying about risks, I would like to note that most of us maybe in the world aren't super into eliminating risks. This is my son from a couple of years ago. I think he was 10 at the time, or maybe 9. He's up at the top of a tree in Amherst, and he's just hanging out there and reading a book. I came home on my bicycle, and there he was at the top of the tree. Why in the world would he choose to be at the top of that tree reading a book, singing to himself? I don't know, because he's not a risk minimizer. That's not what he's doing. He's looking to maximize his enjoyment of life. And my other son here is a ninja. And so he just encounters all kinds of risks and problems, and he ninja chops their faces. So I take a lot of courage from him when I deal with big climate change problems. So let me walk you through hydropower a little bit. And I'll introduce you to these International Hydropower Association guidelines for climate change resilience. Hydropower is amazing. So this is a paragraph that I've got in a paper published earlier this year, and I want to read the paragraph because I think it summarizes nicely what how I think about the ability of hydropower to contribute to our current energy portfolio. There is increasing interest in the development of hydropower as a source of renewable, clean energy, able to increase the penetration of other renewables as a result of its ability to store energy and supply reliable baseload. The hydropower opportunities left underdeveloped since the 1970s are being reevaluated due to a combination of increase in global energy demand, population growth coupled with increasing per capita electricity demand, and the urgent need to decrease greenhouse gas emissions. As a partial solution to the shortfall of renewable energy, hydropower holds great promise. Existing hydropower generation capacity is sufficient to supply the electricity needs of 1 billion people, and only approximately 1/4 of its global potential has so far been developed. So there's a lot more that we can get out of hydropower to solve the world's energy problems. And here's a nice image about hydropower generally, and I just kind of want to look at all the parts of it. So hydropower key facts. In the upper left, we've got hydropower benefits. The worldwide hydropower installed capacity in 2017 is small compared to the total amount of generating capacity. There's what it comes after a terawatt, I actually don't know, 4,000 terawatts of clean electricity generated by hydropower in 2017. That's enough for 1 billion people. Hydropower has one of the lowest life cycle greenhouse gas emissions per kilowatt hour among all energy sources. If the hydropower that's existing on the planet right now was replaced with burning coal, then the GHG emissions, the greenhouse gas emissions, would be 10% higher than they are. 4 billion tons more of greenhouse gases would be emitted. So that means this is the hydropower we've got is reducing our greenhouse gas emissions by 10%. It avoids all kinds of pollution in SOx and NOx. Most of the hydropower capacity is in China, and the United States is in second place. Brazil has quite a lot of hydropower capacity as well, as does Canada. And then lots of other countries come in lower down on the list. And the share of global electricity generation, 26.5% of the electricity is renewable, and of that, most of it is hydropower. Wind power, biopower, solar, all very, very small fractions compared to hydropower. Okay, so we're setting up reasons why hydropower is an important thing for us to be spending a lot of time thinking about. Where is the hydropower located? This is where it's been at. I probably should have switched these slides. This is what we should have had first. This is where the hydropower is mostly located. You can see big centers in Southeast Asia, and also quite a lot in North America, and quite a lot in the Andes Mountains of South America. This is where hydropower is being added quickly, and the numbers are bigger in Southeast Asia. The bubbles are bigger in Southeast Asia and South America and Sub-Saharan Africa than they are in the United States and North America. This is the process that the International Hydropower Association has gone through in the last few years to develop its guidelines. And I won't read all of this the way I did the other one, but I'll draw some highlights. In 2013, the International Development Association, part of the World Bank Group, and its IDA 17 replenishment meeting called for screening all new operations for short and long-term climate change and disaster risks. So this is the same. The way this works within the World Bank is the International Development Association replenishes its basket of money every 4 years. And so the way they do that is they go to donor nations and they ask for more money that essentially is being invested by these nations in international development. And the 17th time they did this was in December of 2013 in Moscow, actually in Russia. And as part of that new investment of all of these countries in the World Bank, they mandated that there be screening for climate change and disaster risks, which was really mind-blowing and set a new precedent that had never been set before. The World Bank signed on to that, and then as a result developed this thing called the Decision Tree Framework in 2015 to outline a pragmatic process for doing that risk screening. And then the International Hydropower Association joined forces with the World Bank thereafter to begin developing their own guidelines, which are really mirrored on the World Bank's decision tree. The European Bank for Reconstruction and Development joined on as well, and they're funding the effort right now. Climate change resilience defined for hydropower here in the middle is the capacity of a hydropower project or system to absorb the stresses imposed by climate change, and in the process, evolve into greater robustness. So not just to survive, but to actually, as a result of going through those stresses, learn and then make improvements so that the stresses are better managed in the future. Here's a few slides on what this climate change problem is that the International Hydropower Association is trying to manage with their guidelines. This is a super basic review, and I won't belabor it, but the atmospheric carbon dioxide has stayed steady for thousands of years, and just in the last 100 years, after the Industrial Revolution, has shot up. Here's carbon dioxide in the atmosphere from the Mauna Loa plant since 1960. The result of that is that temperature has gone up because of this greenhouse gas effect, where the long wave radiation can't escape the carbon dioxide blanketing the Earth. It's caused the temperature to go up every decade. The average temperature is going up a lot since about 1980, 1990, and in the last 100 years, we've got tons of warming that's already happened, like a degree Celsius of warming throughout much of the Earth already. That's all fact. That's all looking backwards. There's no uncertainty in any of that. The uncertainty comes in here in projections for the next 100 years, where we've got these things are called, representative concentration pathways of greenhouse gas emissions. This is saying basically that you could have a very small amount of global warming in this blue area, and this is a small global warming scenario, or you could have a lot of global warming in this high scenario, ending up with lots of warming and a greatly uncertain temperature change in the next 100 years, maybe up to 5 or 6 degrees Celsius of warming over the whole world, and maybe differentially some more warming in some places and less warming in other places. But on average, 4 to 6 degrees of warming in the next 100 years is possible in this high climate change scenario, and low climate change scenario maybe just a couple degrees. So huge uncertainty in what's happening, what could happen in the next 100 years, with ramifications for sea ice and glaciers and ocean pH and all of these things. The effect on the hydrologic cycle that we care about when we're building these infrastructure units on the ground, hydropower or otherwise, is that the higher temperatures speed up the hydrologic cycle. We get shorter rainy seasons and maybe more intense precipitation when it occurs. So the key words are floods and droughts. We get more floods and more droughts. Longer period of drought with stronger bursts of precipitation in between, and glacier snowmelt effects changing seasonality of flow. At the same time, we are losing, both because of climate change and also because of the choices that human beings have to make in response to climate change, our ability to cope with climate change, because we're losing our snow and glaciers where we store water for dry seasons. And we're losing our groundwater storage because as we go through more and more of these droughts and current events, we are mining it out super fast. Urbanization is a huge part of the groundwater mining problem as well. Because of all that, we can end up with a situation something like this. This is a hydropower project in Malawi that we worked on a few years ago. Here is, here's precipitation on the y-axis, and here's temperature on the x-axis. The historical precipitation and temperature from, let's say, 1950 to 1980 is about here. The historical temperature and precipitation from 1980 to 2010 is about here. Let's say maybe that's a trend. I don't know if that's a trend, but it's worth noting that it got a ½ degree warmer in that 30 years than that 30 years. And maybe there's a tiny bit less precipitation than there was in the middle of the century. Maybe it's going to go back up, who knows? It's worth monitoring, but we take note that in these 30-year chunks, it seems to have gone in this direction. If we built a hydropower plant for this kind of climate, we would expect there to be about 1,000 millimeters of precipitation. Unfortunately, all of these GCMs give us huge amounts of, push a button early, huge amounts of uncertainty in what the future precipitation is going to be. If we built expecting there to be 1,000 millimeters of precipitation, and all of these GCMs up here with all their uncertainty, we saw the uncertainty band before in temperature of that there could be 3 degrees up to 6 degrees or something of warming. Well, there could be more precipitation or there could be less precipitation. And if we build for historical precipitation in Malawi, and any of these global climate models are correct, then we would have undersized our project. And if any of these global climate models are correct, we would have oversized our project. We would have we would have spent too much money building a project that isn't justified because there's not enough stream flow to generate the hydropower to pay off the capital investment. With this sort of uncertainty, with these GCMs coming in all over the map, what can a project manager do? If you want to build a hydropower project and you've got all this massive uncertainty from climate change, what can be done to increase your confidence that you're building the right size? Investments in the water sector are potentially significantly impacted by climate change. There's no consensus on future climate. You could have more precipitation or less. Guidance is needed. So in response to that IDA 17, the International Development Association 17th replenishment in Moscow, Russia, we developed this thing called the decision tree. And here it is. It's a phased, hierarchical process walking through initial project screening and a desktop analysis and a climate stress test, which is really decision scaling developed at the University of Massachusetts by Casey Brown and all of his team over the years, up through climate risk management, which involves maybe higher level algorithmic approaches, including genetic algorithms and dynamic adaptation policy pathways out of the Netherlands, or all kinds of cool algorithms for dealing with, for finding an efficient development path through climate change risks. We published it in this book called Confronting Climate Uncertainty in Water Resources Planning and Project Design, and that's available for free to download from the World Bank Open Knowledge platform. And this is the process that the International Hydropower Association guidelines is based on. We've done lots of case studies of this type of process all over the world. We're working with Ohio River floods and Nepal hydropower and Malawi hydropower, the Brahmaputra Water Energy Food Nexus, Mexico Integrated Urban Planning, California Water Supply Management. So many things that stories to tell. I have so many stories I'd love to tell. But for now, we'll focus just on this Nepal hydropower. So here's an example from Nepal. And this is going to try to walk through for you how we apply this sort of decision tree slash International Hydropower Association guidelines process to a real life case. So in Nepal, in short, there's an intense mismatch between electricity system demand and generation. They've got, forgive the weird months here. This is in Nepal, they structure their calendar differently than we do in the West. And this bit here, where you've got a lot of blue, that's the middle of the summer, when there's a lot of monsoon water. So lots of monsoon water here, lots of monsoon water here. And the dry season down here is actually the winter months like November, December, January, February, and here is the bottom when there's no rain. The red line represents energy demand, which is pretty constant throughout the year, and in fact goes up a little bit in the winter when they're running their electric heaters to keep warm in the mountains. And so the motivation from this is to build a lot more electricity generation capacity to solve this mismatch, the seasonal mismatch. Here's an Ethan Yang plot, if he's still on the line. Another shout out. Ethan's getting lots of shout outs in this presentation. So here is a map showing the location of this particular hydropower plant. This is called the Upper Arun Hydropower project, and it's right here, right next to the boundary between Tibet, Chinese Tibet up here, and Nepal down here. So this gray line shows you where Tibet to the north interacts with Nepal to the south. And what you can see from this red basin boundary is that almost the entire basin is in Chinese Tibet. And this sort of bigger basin that it's a part of, called the CUAHSI Basin, is located largely inside Nepal. Also, Mount Everest is right in here. So crazy elevation gradients located within this basin. For this particular project, this is a priority project of the Nepal government. And they for sure know that they want to develop this red line here. This red line is 335 megawatts. And we plot it like this to show that this is the gigawatt hours per day produced. And you can look at this black line and you can think of just stream flow because there's no storage. So the ability to produce hydropower every day is a direct calculation from the stream flow that's available coming down from the mountains. So in the monsoon, it goes way up, and in the dry season, it comes down. Monsoon way up, dry season way down for about 25 years here in a row. And the red line shows that they've designed by default a project size that is highly robust to stream flow variation. They call it Q70, which means that it's reliable 70% of the time. It will produce at capacity 70% of the time. So the black lines here go below the red line about 30% of the time. And so you can see that whatever happens to stream flow, it's likely that you're going to be able to produce pretty much all the hydropower that you can all the time. But what you also see is that you sacrifice the ability to produce a lot more in the summer monsoon season, because you have to let it just spill over. You can't fit it through your turbines. There's other design sizes, the orange, the yellow, the green, the blue, that get successively bigger, 335 down to 2,000 megawatts, a Q25. Q25 is fully reliable 25% of the time. So these are the choices they're faced with. They know they want the red one, but they think they might want some bigger ones. And they asked us to do an analysis to look at the climate vulnerabilities, not just of the red design, but these others as well. And we have to factor in all of these other things like its cost and its how well it handles sediment, which we call a plant load factor, discount rates on the loan they're going to get, which matter a lot. That could be a whole talk in and of itself. The selling price, that it matters when you're selling the electricity in the monsoon season or not, and how long they think this thing is going to operate. The way we go about analyzing this is to run it through a hydropower model. Let's start with the hydropower model and work backwards. We have a pretty simple equation for a run-of-river facility without storage that translates stream flow into hydropower produced. And that hydropower produced maybe becomes money as well, so we could put a financial model on the back end of this as well. But let's stop with hydropower for a moment and then say we need stream flow to put into that. So the stream flow that we put into that comes from a hydrologic model. The hydrologic model tells us, under all kinds of different climate conditions, how much stream flow is available for the hydropower model. Well, how do we run a hydrologic model? We need to examine all kinds of possible climate conditions for our hydrologic model to process. How do we generate those climate conditions? We can generate them quite directly using this thing called a weather generator that does as fancy as you want bootstrapping, resampling on the historic record. The way we did this was quite simple, actually. We just resampled on the historic record, separating monsoon and non-monsoon season, and combined them in all kinds of different ways. It was really a seasonal bootstrapping technique for running our hydrologic model and our hydropower model. And when we run these things many times, maybe a few thousand times, we can trace out green zones and red zones of good performance. And all you have to do is set some sort of a threshold, which the stakeholders can set, that say there's some sort of amount of hydropower produced that we call acceptable. And let's say you produce an acceptable amount if you get a lot of precipitation. And there's some amount of hydropower produced that we call unacceptable and that's the amount of hydropower you produce if you don't have enough precipitation. You can trace out this sort of climate response surface. A key to this whole thing, this is a figure made by Sung-Wook Wee at the University of Massachusetts, a hydrologic model with a glacial component. One of the keys to this whole thing is that we can satisfy ourselves that we can represent the hydrologic behavior of the basin as well as possible for that particular basin. And this particular basin, of course, with its significant glacial component, needed a glacial module that kept track of the energy transfer happening as well as the water transfer happening from upstream to downstream. So we had that model. That model was calibrated in at three stations that gave us some measure of confidence. Here's station 1 and station 2 and station 3, and they all have these nice Nash-Sutcliffe values, so we feel pretty good about our calibration. And that calibration gives us this sort of information. This is where it starts to get really meaty for us about what we can learn about this basin from our hydrologic model. That for each year in 1986 up through about 2005, when we had data to calibrate and validate this model, we can begin to partition, if we believe the output of the hydrologic model, again, without testing really where the water is coming from with an isotope test or something. We're just partitioning it based upon what seems physically reasonable inside a model that we may or may not believe. In this case, we think we do because we have a good calibration. For where the water is coming from precipitation or from snow melt, could also be glacier melt in this case, or from groundwater. And the big lesson we take from this hydrologic modeling result is that we think we know when the snow melt and the glacier melt is contributing most to the stream flow. And we think that that's happening between March and June or so. That this is the time when a lot of the flow is coming from snow melt and glacier melt, and that has a huge climate change ramification. This shows us what is likely to be impacted most quickly and most directly by warming temperatures, that this stuff may shift lower in the year. And this stuff may go up for a while we're melting the glacier until the glacier gets melted down and goes away. When we run our hydrologic stress test, that calibrated hydrologic model many times, we get a result something like this. This top one is for the total annual, and this is the dry season, and this is the wet season. Let's focus for a moment on the total annual. The total annual is a really wonderful, interesting finding. Here is our precipitation on the x-axis, and here's our temperature on the y-axis. This is our historical point at 100% of historical precipitation and no warming. So this point right here is the intersection of our red and blue, right? Because we're saying blue is more stream flow than historical and red is less stream flow than historical. So those red and blue come together at the historical point. If all we do is go straight up and we add warming and we do not change the precipitation, let's remember that our precipitation forecasts say that lots of the projections say there could be less precipitation, and lots of the projections say there could be more precipitation. We don't know. But almost all the projections say there's going to be more warming, let's say somewhere between 1 and 4 or 5 degrees in this zone here. Well, a fascinating thing happens if you add a lot of temperature to this basin. You get more stream flow out of it. It actually becomes a better hydropower producing basin the warmer it gets, up to about 3 degrees Celsius warming relative to historical. That's a fascinating finding of real interest to hydropower investors in this basin who think that maybe they should be planning for more stream flow than they've had historically. This analysis looks only 30 years into the future because it looks at what we call the economic lifetime of this project, and the term of the loan is only 30 years. So that's a really interesting thing to evaluate. If we want to look at this project 100 years out, this result would look really different. But for the sake of the investor in the project, this is what the result looks like. It looks like even better stream flow conditions for hydropower in the next 30 years. All right, fine. So if climate change doesn't appear at first glance to be a real risk for this project, and might even possibly be an opportunity, then we should look at other possible risks as well. We should look at construction time and lifetime and sediments and seismic risk and cost and discount rates, cost overruns maybe, or operation and maintenance costs that are higher than we expect. So we do that. We made like 500 socioeconomic, we call them socioeconomic scenarios. They're just scenarios of these combinations of these things. We added in 13 what we called representative flow scenarios because we were starting to get to a crazy number of scenarios. So we didn't do tons of flow scenarios. We just picked representative ones on their variability and mean. We evaluated the net present values of all these scenarios. There's about 6,500 plausible futures. We used Latin hypercube sampling to make sure that we got a well-representative sample. And we got a result, well, sorry, I jumped the gun on this. This is still just a climate change result. I guess this is a little bit out of place, should have come just before I talked about the last thing. So finishing up on the climate change result, we saw that with a bit of warming, you're likely to get more stream flow and likely to have a better hydrologic condition for hydropower. This says that in fact, even if you have a worst case scenario, which is it doesn't warm at all, meaning you don't melt your glaciers any faster, and you have actually 40% less precipitation over here, 40% less precipitation over here, and no warming, you still have this blue color. There is no red, right? Remember we were looking for the red, we were looking for that threshold. Well, the threshold is you lose money on this project. In which situation do you lose money on this project? And you never do in this case. You still have a net present value of about $300 million, even in your worst case scenario. That's because this project, that 335 megawatt design capacity project, remember, was a very robust conservative design that was likely to perform well under a wide range of stream flow conditions. And if we put all the GCM projections on there from all the representative concentration pathways, we get an expected region in here somewhere, which means that we're likely to have something like $400 to $600 million of net present value from this project. Looking really good. Okay, so then we look at all those other uncertainties and we start to ask ourselves, how will this project, if this project isn't really sensitive to climate change, then what is this project sensitive to? So here is this range, right, from about 300 million to about $800 million of net present value. Look at this. This is exactly the same thing. So this is what's called a parallel coordinates plot. And this is the type of thing that we like to make when we have lots of dimensions of uncertainty that we want to evaluate, in addition to just like the 2 dimensions or 3 dimensions that we can put in a surface plot. So here we've got our change in precipitation and our change in temperature that you saw on the last figure, but we've added more coordinates. Now we've got the economic life as well, and the plant load factor, which is a surrogate for sediment load. This is how much the sediment damages the turbines. Now often you have to turn the turbines off to clean them and flush them and repair them. The capital cost, of course, is how much we overrun our initial capital cost estimates, and our price is the possibility that we could sell our electricity for higher prices than we're assuming we can, the current prices, and the discount rate is the terms of the loan. So when we select all of the possible changes in precipitation, all of the possible changes in temperature that we've put the exact same ranges that we've gotten here, you can see precipitation goes from 100% of historical to 40% more, 100% of historical to 40% less. Temperature change goes from 0 to 8 degrees Celsius. Same thing here, temperature change from 0 to 8 degrees Celsius. Delta P from 100% to 40% more, 40% less, all selected, and the range is $300 million to $800 million. Okay, but there's all this other uncertainty in our results from net present value. What does it come from? What if we expand the uncertainty in economic life? If we expand the uncertainty in economic life, meaning, what if this thing could live longer than 30 years or less? Does that really impact anything? We went down to 21 years and we went up to like 36 years. Does that change much? It fattens the line a little bit, but it doesn't really give us a lot more explanation of our uncertainty, right? It becomes a little bit more, it covers a little bit more of the uncertainty, but not a ton. What about capital cost uncertainty? Put economic life back and expand capital cost uncertainty. Now we're getting somewhere. Now we see that if your capital cost doubles or triples, you could really lose money down to a net present value of negative $1 billion. And what about if we could sell more? Now, why are we evaluating the possibility that we could sell more? Because, as I mentioned before, maybe it all rides on our ability to cooperate. There is an agreement that Nepal is trying to establish with India to sell their hydropower to India and then to buy coal-fired electricity from India. If they did that, there's possibility that they could maybe sell for a higher price than they're selling just to Kathmandu. So maybe they could sell for higher. If that sort of agreement becomes possible, then maybe they could really have a real boon day with this hydropower project. So we see that the explanatory factors for this project, the uncertainty dictating risks and opportunities on this project, really have more to do with capital cost and price than they do with climate change. When we evaluated that type of uncertainty for all the project sizes, this is all those project sizes we saw before, 335, 750, 1,000, 1350, 2,000. We try to evaluate them in as many ways as possible. So let's look at these 4 different things we're evaluating. The fraction of all the scenarios in failure, the 2,000 huge facility fails in more than half of all the scenarios that we evaluate. The small one fails in only about 10%. So this smaller plant doesn't fail as often. But what about maximum regret? When it does fail relative to the others, it fails big, $5.73 billion of regret. And the bigger one doesn't fail as bad. Mean dry season hydropower produced, you get a little bit more hydropower out of every bigger size you produce, right? The question is this increase in mean dry season hydropower production, is that enticing enough to cause you to take on more risk? And then your net present value is not that different in the median sense across all of these. But some of them, you get these outliers. If climate change really melts those glaciers fast and you get this big one here, you could really make a lot of money. So as a result of this analysis, this is really cool. I just learned this a few weeks ago. The Upper Arun Hydropower Company is reconsidering whether they want to build the 335 megawatt one. They're really homing in on a 750 megawatt one because they think that they get much better mean dry season hydropower, and they maybe get significantly better possibility of higher net present value, and they don't take on too much risk. So that was really cool. It's not too often that we get to see real change made based on our analysis, but I think that they are really shifting what they're planning on doing based in part on this analysis that we've done for them, weighing costs and opportunities, risks and opportunities. This is some work I've been only peripherally involved in, and I just wanted to give a shout out to Anthony Herford and Julian Haru from the University of Manchester in England. They were a part of this analysis, this Upper Arun analysis, and they expanded it to include all of these other hydropower projects that are scattered throughout this CUAHSI basin. So remember, the Upper Arun basin is this one that is just this bit like this, right? But it's part of this bigger CUAHSI basin that includes these other wings along here. And so they did an optimization framework to figure out which portfolios of investments in hydropower projects, not just various sizes of the Upper Arun, but the Arun 3 and the Dud CUAHSI and the Upper Tamar CUAHSI and all these guys. How would we combine all of these in the most efficient way? Like, what's a good portfolio of investment in hydropower? There's the Upper Arun there, and they come up with something like this that shows that clusters of investments in run-of-river dams, including maybe the Dud CUAHSI, but not necessarily the Sun CUAHSI, give you the best possible net present value and lowest possible maximum net present value regret. So that's pretty neat. So what they're saying is, sure, build the Upper Arun and other run-of-river projects, but add the Dud Koshi and you'll be in really good shape. Maybe skip the Sun Koshi. Kind of cool, right? So this reminds us that we should not get so myopically focused on one project at a time, but keep our eye out to the benefits to be gotten by developing the whole basin together. All right, so takeaways again from this talk. Hydropower has obvious negative attributes, and it also has often underappreciated qualities of essential importance to our climate change problem. And that means it can really help us to give the needed whatever it's called, electricity base that's needed for other renewables like solar and wind that can't produce, base load, not base flow, the base load needed to support those renewables that change so much with the sun or the wind. The International Hydropower Association has been developing these guidelines, and they are based on the decision tree framework from the World Bank from a few years ago. This was a demonstration sort of how process using those guidelines would work. Vulnerability to climate change is not necessarily the most vulnerable part of the project. It might be much more vulnerable to the treaty that could be made between Nepal and India, for example, or the possibility that capital costs would get overrun. Capital cost expectations would go up. And we want to emphasize bottom up in the way we do these types of analyses to understand place and context as well as possible, because that gives us the best chance of understanding the risks of a certain place. If we just take climate change projections from all over the world and stick them on the Upper Arun project in Nepal, we might really miss what the real vulnerabilities are. And to throw my religion into the mix, because I always love to throw my religion into the mix, it usually always rides on our ability to cooperate. And if Nepal could cooperate with India on electricity sharing and really seal that deal on dry season versus wet season, hydropower versus coal, I think there's huge opportunity for both nations to benefit. Here's those pictures of my kids again, because I like showing pictures of my kids, reminding us that we don't need to be afraid. That's it. Thank you.
Thanks, Patrick. Really appreciate that presentation. Does anyone else listening in have any questions for Patrick? If you do, you can type them in and I'll read them off. Oh, I see a question. Okay, so this question is, what hydrological model do you suggest for the assessment of climate change on a river basin where glacier melt and snowmelt combination is high? Yeah.
I love that question. Yeah, let's see if I'm still in here. So here is, I'll just bring us back to the schematic of the, you know why I love that question? Because just today I had an argument with somebody about that question. I'm doing another analysis. The short answer to the question is I don't have a strong recommendation. I think that what we need is, I think the question was specifically for high mountain regions or something. You know, we need to have a really good accounting of snow and glacier stuff. So this is a high mod model that Sungwook tailored and developed for the Himalayan region for Pakistan and Afghanistan, and also used in Nepal. So high mod is fine, but we just want to have a good accounting of snow and glacier. There's one SPHY that I'm teamed with a team from Deltaris, company in the Netherlands, and a company called Future Water. They're really awesome at this stuff. They've got a SPHY that they use for the Himalayan region. I've never used it before, but we are using it for another assessment in Nepal, and they claim that it's really awesome at that, at high mountain snow and glacier stuff. I haven't seen it myself yet, but I'm excited to see it used for those purposes. I guess one thing I would say is that you know, the real problem here is probably not the accuracy of the hydrologic model, it's probably a lack of good data. So when we do these assessments in high mountain regions, we often have such crappy data that it probably doesn't matter that much just how fancy your hydrologic model is.
So kind of piggybacking off of that, then for the study you presented in Nepal, how did you guys had stream flow data, but how did you have any other means of verification, any snow information or?
Yeah, man, no, no, short answer is no. And measuring these glaciers, you know, we might have some sense for the spatial extent of the glaciers, right? From I don't know how exactly how you get that from satellites or from flyovers. I'm actually not sure how people know the spatial extent of glaciers, but we can have a reasonable sense for like the square kilometerage or square meterage of a glacier, but it's extremely uncommon to have a good sense for the depth of the glacier, the actual volume of the glacier. So that's you know, it's problematic. We have a hard time knowing exactly how much ice and snow is there to begin with. Maybe
Yeah,
the
and
punchline
following
to
up.
that is, I'm sorry, go ahead, Catherine.
Oh yeah, go. No, what's the punchline? What's
Well, punchline is do a sensitivity analysis on that. You know, like see,
mm.
include that in your uncertainty analysis, the actual snow and glacier available for stream flow.
And then yeah, so the same person who asked the original question wanted to know about the second model you mentioned, SPHY, I think. Their question is there more uncertainty in that model, and would you suggest that model for doing research?
I suggest that you look into that model. So I haven't used it yet myself. The company is called Future Water, and the famous glacial hydrologist who participates in that company, he has some particular role in that company, and he has helped develop the model, is named Walter Immerziel. And that's the guy that gets a lot of respect around the world. So I would say, based on the weight of his name, I would certainly look hard into that SPHY model. But again, I haven't, if we talk again in 6 months, I will be able to tell you my personal experience with that model, but I just don't have any yet.
All right, that's a good answer. Is there any other questions people have? Yes, we have a question. Have you done similar analysis for any cold region river basins? How do you think the river ice could affect hydropower in those places?
Yeah, these are really good questions. I've been a part of, so the short answer is I'm totally unqualified to answer that question, but that won't stop me from trying. Watch this. But I've been a part of, yeah, so the answer to the question is no, I haven't done these assessments really where there's a significant amounts of river ice. But I have been a part of conversations with the International Hydropower Association, and especially the guys in Hatch Hydropower, a big powerful hydropower company in Canada, and they think a lot about that stuff. And they have concerns that, yeah, the ice behavior will change in a way that they have to rewrite their operation manuals and things for how to deal with the ice with climate change. They just don't know how to anticipate what the changes will be and what to tell the operators for standard practice. So yeah, that's something that they think about, but I don't have a lot of personal experience with that myself.
Do you know of any research besides academic research going on that topic at all, or just that particular company that you mentioned?
You mean the river ice question?
Right.
No, I mean, except to point to the Canadians. The Canadians do a ton of hydropower, and they're thoughtful folk. They're nice folks, and I know that they take this type of stuff seriously, and they've got all kinds of manuals for how to deal with river conditions. So I'm sure that I would check out Hatch. What's that? I can't remember the name of the other company. I'm blanking on it, but the other big hydropower company in Canada.
Is it Hydro-Quebec, or is that?
Hydro-Quebec is interesting.
No.
Yeah, that's not the one I was thinking of. But yeah, there's
Okay.
another. Yep. Yeah, so I would definitely consult the Canadians who spend a lot of time dealing with hydropower in very cold places. I think their companies might have user manuals or some kind of reports, annual reports or something. And if
Great.
anybody wants me to try
Yeah,
and connect
that's
you to somebody, I have reasonably good contacts with Hatch. So you could contact me
cool.
later to ask me for that.
Yeah, that's really interesting. I hadn't thought about that issue. Any other questions from people listening in? Give it a moment. All right. Well, thank you very much, Patrick. Really appreciated your presentation, and thanks for everyone else for listening to the series. And I hope you've enjoyed it, hearing about these major challenges in river basins around the world. And really appreciated you ending the series for us, Patrick. So thanks much.
Well, thank you so much. It was really fun. Glad to be here.
All right.